AQA, A-level physics. This is for the electronics option. And this video is about operational amplifiers. So what is an op-amp? It's a chip. It's an integrated circuit. So there's lots and lots of different transistors and resistors all on this chip, this piece of silicon. Okay, it's an integrated circuit. And what it does is it amplifies the voltage difference between two inputs. So there's two inputs called the non-inverting input, which is positive, the inverting input, which is negative, or it's labeled positive and negative, and then you've got your voltage output. Sometimes the positive is on top there, sometimes it's on the bottom. It doesn't really matter. It depends on how convenient it is for the particular circuit that you're drawing. But usually you've got the non-inverting above and the inverting below. Two inputs and an output that we're interested in. Originally they were designed to do kind of mathematical stuff in analog computers before digital computers. So mathematical operations, so op-amps, that's why they're called op-amps. Very common type of op-amp is the 741. There's lots of others. And so this chip has this circuit called an operational amplifier built into it. And you look at the data sheet when you buy these chips and it'll tell you what all the different connections are. And you've got the power supply inputs as well, V plus and V minus. Now, an op-amp can run off a dual rail power supply. So a dual rail power supply, you've got, like, for instance, here there's plus 15 volts and minus 15 volts as well. There'll also be a zero, which is your earth as well, which you may or may not use. Now, note that the value of the voltage out, V out, can't be bigger than 15 volts. Okay, so V out will be limited to plus or minus Vs. Now, when we haven't got any other resistors or things connected to the op-amp, the gain of the op-amp, which we call the open loop gain, is very, very big, maybe about 100,000 times. So when I said V out is proportional to the difference between the two voltages, and this here, AOL, is my open loop gain, which is very, very large. In an ideal op-amp, it's actually infinity. Now, this doesn't mean that V out is going to be ridiculously big or equal to infinity, because remember that it's limited to plus or minus the power supply. So basically, if V plus is a little bit bigger than V minus, then the output will be plus 15 volts. Otherwise, it will be either zero or whatever. So remember that the output is limited to plus or minus Vs. Op-amps have a very high input resistance, a bit like our MOSFETs. That means that they draw almost no current from anything that they're connected to. For example, some kind of a logic gate. Okay, they don't change the voltage that they are detecting. The difference between the two inputs, so the difference between the voltage at the non-inverting and the voltage at the inverting input, is always very, very small. And in fact, what we do is in our little analysis, we assume that it's actually zero. So the difference between the voltage at the two inputs is always very, very small. So these are the different ways that we can use an op-amp that we need to know about. We need to know about a comparator, inverting amplifier, non-inverting amplifier, summing amplifier, and difference amplifier. And I'm going to work my way through this. And I know if you've not seen this before, it'll look very, very ominous, but don't worry, all will be revealed. Okay, so first of all, the comparator. Now remember that V out is the open loop gain, which is ridiculously big, times the difference between the voltage at the two inputs. Now looking at this circuit, at the non-inverting input, which is the V plus, there's my V in, that's my voltage going in. At the inverting input here, we have a reference voltage. I mentioned reference voltages when we talked about Zener diodes. In this case, the reference voltage is just provided by a potential divider. So it'll depend on the value of these two resistors. A fixed voltage, a reference voltage. And if V in is bigger than the reference voltage, then V out will equal the plus supply voltage. If it's less than, then it will be minus the supply voltage. So this is using the op-amp as a comparator. We're comparing the two voltages. If V in is bigger than V ref, then V out is plus Vs. If V in is less than V ref, then V out is minus Vs. So look at this. Here's my comparator. An op-amp runs off a plus or minus 10 volt power supply. Both resistors are 10k. If the AC signal shown is input into this circuit, how will V out vary with time? Well, if both of the resistors are 10k, then V ref is going to be 5 volts, isn't it? Yes. And so basically, if V in is bigger than 5 volts, so anywhere that V in is bigger than 5 volts, then the output is going to be plus Vs. Otherwise, it will be minus Vs. So my output voltage will be this. Yes. So V ref is 5 volts. If it's above V ref, it's plus 10. If it's less than V ref, it's minus 10. Look at this circuit. Explain what this circuit does and how it works. Explain the function of the variable resistor. So, do you want to have a think about this? See if you can figure it out for yourself. So, V ref is there. Yes, and again, you've got a potential divider which will determine what V ref is. Here, V in, you've got another potential divider. There's your other potential divider. And this resistor is a thermistor. And so basically that resistance depends on temperature. If it gets hot, then that temperature, if the temperature is big, then the resistance of the thermistor is small. So V in will get bigger. And so if we adjust the value of the reference voltage, we can have it so that when it's hot, this voltage here goes above the reference voltage, and maybe it turns the bulb on. Yeah, the op-amp is being used as a comparator. When the voltage at the non-inverting input, yes, is greater than the inverting input, which is the reference voltage, then V out is 10 volts and the bulb lights. If not, then V out is 0 in this case, because my power supply is connected to earth. Then it's 0 and the bulb is off. The resistance of the thermistor will fall with temperature. At a certain temperature, V1 will be bigger than V ref and the output will be 10 volts. This could be used in your fridge. If the fridge is too warm, then maybe an indicator or an alarm will go off. And adjusting the variable resistor alters the reference voltage. Okay, the inverting amplifier now. Now we have some more resistors. We have this resistance here from V out going to V2. Now notice that I've got the negative at the top here. So this resistor goes around back to the inverting input. Yes. We say that part of the output voltage is fed back and added to the input. So some of the voltage is fed back to the input So this is actually called a feedback resistor. So it's called RF. Yeah, F for feedback. The closed loop gain is now, it's not infinite. The closed loop gain is minus RF over Rin. RF is the feedback resistance, Rin is this resistance here. And notice that it's minus, and this is why it's called an inverting amplifier. So the gain is actually negative. So what it will do is it will amplify Vin, but also invert it. It'll change it from positive to negative or vice versa. Now, you need to be able to derive this equation, and it's actually pretty straightforward. So look at this. I'll have a go at deriving it. Now, because it has a very high input resistance, there's no current flowing into the op-amp. So any current that comes in here will flow straight to there. Okay, if V in is bigger than V out, then any current will flow that way, and the current through the two resistors is the same. Now, the voltage difference between V1 and V2, we said will be virtually zero. We're going to assume that it's zero. So if V1 is earthed, then V2 is also earthed because of this assumption, and we say that it's a virtual earth. So at this point here, that is a virtual earth. I mean, this point here is earth because it's earthed. Yeah, that's zero potential. And because V1 and V2 we assume are the same, V2 is a virtual earth. Looking at the top two resistors together, the difference in voltage between V in and V out is V in minus V out. The resistance of that top bit is R in plus RF. So my current I is V in minus V out over R in plus VF. Straightforward. Now, if we look at them individually, then this current here, I, is going to be V in minus 0, because remember V2 is a virtual earth. So V in minus V2 equals over R in is the current, where V2 is 0. Yeah, that's we're going to say that's 0. And for the other resistor, V2 minus V out, and remember that's 0, V2 is 0. So V2 minus V out over RF is the current. So if I put V2 equal to 0 now, so V in minus 0, which is just V in over R in, yes, V in over R in, equals 0 minus V out over RF. So that's minus V out over RF. Rearrange that. So my gain, which is V out over V in, is minus RF over R in. Don't worry about the top line. I think you'll get away with just learning that. Make sure you understand that, and you can regurgitate that in an exam with reference to the diagram and the virtual earth. You need to understand this idea of a virtual earth. This is what an inverting amplifier would do. So my gain, remember the gain is minus RF over R in. So looking at the values of the resistors, my gain will be minus 2. And so that means V out will be twice as big as V in, but it will be inverted. And if you look at the graph, that's what's happening. This is a non-inverting amplifier. So looking at this, V in is going to the non-inverting input. Notice it's back up the top now on this diagram. And my feedback loop now is down the bottom here from the output going to the inverting input. Okay. The gain equation is different. For one thing, it's positive, it's not negative. You don't need to derive it, it's on the formula sheet. So the gain for the non-inverting amplifier is 1 plus RF over R1. The advantage of that configuration is that this amplifier has a much higher input resistance. If you go back and look at the circuit for the inverting amplifier, the input resistance for the inverting amplifier is Rin plus RF. The input resistance for this amplifier is almost infinite because it's the resistance of the op-amp itself. And that means that this will draw a lot less current from the input source, so it's less likely to change it. This is a summing amplifier, and basically it adds together V1, V2 and V3. So V out is, and there's the equation, notice it's inverting. V out is that. And if you have these as variable resistors, then you can change the amount that they contribute, yes, to V out. So this could be an audio mixer. You could have, there's the first guitar, there's a second guitar, there's the vocals, and you twiddle the knobs and change how much they contribute to V out. The fact that it's inverting doesn't matter for an audio signal. You wouldn't be able to tell if it was inverted or not. Okay, so that's a summing amplifier, and you're given the equation if you need it. This is called a difference amplifier, and this amplifies the difference between V1 and V2, but the gain is RF over R1. So it's not like a comparator. The open loop gain of a comparator was like infinite. Here, the gain is RF over R1. So, and it amplifies the difference between V1 and V2. Now, there's an interesting use for this difference amplifier. And if you're a musician, if you play guitar or sing in a microphone, you'll know that a good microphone produces a balanced signal. Now, what does that mean? Well, it means that it actually gives you two signals which are out of phase with each other. So you sing in the microphone, and in the microphone cable, you've got both of these signals which are out of phase with each other. Now, as these signals travel along the cable, they pick up some noise, yeah, which is usually like 50 hertz hum from amplifiers and power supplies and things. But both of these signals will pick up the same noise. And so the clever thing is that if you get these two signals and you put them through a difference amplifier, then that amplifies the difference between them, and so the noise disappears. Because the noise is on both of them, so that isn't amplified. So all you get, your output, is the difference between the two signals, which is your original signal. Sneaky. So at the mixing desk, the two signals go through a difference amplifier, and when the difference between the two signals is amplified, the noise disappears. So that's a use for a difference amplifier. Very interesting. So these are the op-amp configurations that we need to know. The comparator, the inverting amplifier, the summing amplifier, the non-inverting and the difference amplifier. Be able to recognize them, okay? Be able to recognize them. The only equation that you need to worry about is for the inverting amplifier. The other equations, you'll be given them, well, they're on the formula sheet, basically. One thing is that the circuit will be in an unfamiliar context. There'll be maybe one or two other sensors at the input. There'll be maybe some stuff on the output side. My advice would be look at as many past papers as you can and you'll get used to it, okay? If it's very new to you, then I imagine you've probably got a nosebleed now. But if once you've started looking at some examples, you'll see that it's pretty straightforward. Just recognize the different configurations. It's pretty obvious if you've got like these things here going into the same input. That's a summing amplifier. If you've got a couple of things going into different inputs, that's a difference amplifier. If you've got one of the inputs, well, this input here is earthed, that's an inverting amplifier. If the signal's going straight into the non-inverting input, that's a non-inverting amplifier. If there isn't a feedback resistor, that's a comparator. So we've been talking about ideal op amps. Now, real op amps, real life op amps, there's a limitation which we need to know about them. And it's to do with the frequency and the relationship between the gain and the frequency. Now, for the open loop gain, now remember that we don't usually, apart from a comparator where frequency doesn't really matter, we don't use the op amp with an open loop. There's always like a feedback resistor, so it's like a closed loop. But nevertheless, the open loop gain varies with frequency. And if you look at this graph, now note that it's a logarithmic scale, so it's going up in powers of 10, and the gain is going up in powers of 10 as well. But nevertheless, the gain above 10 hertz starts to fall really, really rapidly. Yes, and as I said, bear in mind it's a logarithmic scale. So the gain here at a very, very small frequency is very large, and then above 10 hertz, the gain falls very, very rapidly. And we say that there's a characteristic of an op amp, and we call it the bandwidth. This word here in electronics, we'll see, is a bit confusing because it's got so many different meanings, the bandwidth. But anyway, the bandwidth, what do we mean by the bandwidth of an op amp? Well, it's the frequency above which its open loop gain falls to 0.707, which is 1 over root 2 of its maximum value. Okay, so at this point here, the open loop gain, is 200,000, and then when does it fall to 200,000 divided by root 2? Well, on a logarithmic scale, it's actually only about there. So that the bandwidth of my op amp is that frequency there. Okay, so the bandwidth of an op amp is defined as the frequency above which its open loop gain falls to 1 over root 2 of its maximum value, which is about 10 hertz. Okay, now the closed loop bandwidth is much, much higher. It's about 2.5 megahertz. That's when the gain of the circuit equals 1. Okay, again, the gain will depend on the bandwidth, or the bandwidth will depend on the gain. Yes, and it's much, much higher for closed loop. There is, when we're using an op amp in a circuit, like in an inverting amplifier, there's something we need to know called the gain bandwidth product, or the GBP. And the GBP for a particular op amp is constant. And the GBP, the gain bandwidth product, well, the clue's in the question, it's the gain times the bandwidth. So the gain times the bandwidth is constant. That means that if we had a gain of 1, yes, if the gain was 1, now how would you have a gain of 1? Well, if RF is equal to Rin, and if you remember the equation for an inverting amplifier, that means the gain would be 1, then the bandwidth would be about 2.5 megahertz. Yeah, 2.5 times 10 to the 6. So the gain bandwidth product would be 2.5 times 10 to the 6. If we made the gain bigger, then the bandwidth would be less. Okay, if the gain, for example, if the gain was 10, then the bandwidth would be 0.25 megahertz, wouldn't it? 250 kilohertz. Now, this fact that the gain goes down with frequency shouldn't be a problem for audio signals, because audio signals are very rarely above 20 kilohertz because humans can't hear above 20 kilohertz. So that's a much, much smaller frequency for it to be a problem to affect the gain. Other communication signals might suffer, like very high frequency signals might suffer a bit from loss of gain.